So let me just tell you a bit of the plan. So we, depending at the speed we can go, and I mean we don't have to rush. I'm hoping to cover sort of all the core material or the core techniques by the end of this week. This would be the hope. We'll see. So by this I mean finishing residue calculus, doing the argument principle, and then Taylor series and Lorentz series. I mean, the idea being that in order to talk about Taylor series, we need to talk about convergence of right. We need to talk about convergence of sequences of analytic functions or series of analytic functions. So we'll talk a bit about when is it that a sequence of analytic functions, when it converges to a limit, when is it that we can make sure that the limit is also an analytic function, right? Because then this will allow us to talk about, for example, Taylor series, right? We talked about power series already, but right now will allow us to do this with other types of series that are not necessarily power series, and in particular will allow us to immediately get the Taylor series by writing it in the expansion that we already had, sort of this truncated Taylor series, and using those theorems to argue that indeed it must converge. Then we'll do, right, so this will allow us to talk about sequences and series of analytic functions. The residue and calculus and argument principle will allow us to do lots of calculations over integrals, even integrals over the reals and definite integrals and so on. So you'll see a lot of this in exercise class. Okay? And then sort of just one more ingredient basically is the idea that if you have a function that right, that has maybe a pole somewhere, right? Think of a function maybe it has a pole at 0, for example. Then, right, taking a Taylor series might not seem like a good idea. But you can take, we can take a series on the variable 1 over z, right? And so this will allow us to define sort of a Taylor-like series for domains where you have, the function is defined in an annulus, say, right? And so this will be the idea of Lorentz series and will allow us to do something like a power series, right? Both in a way, both in the variable z and the variable 1 over z for a function that, for more functions, and will allow us to use Taylor series like things even for functions sort of that may have a pole somewhere and then for which Taylor series won't quite work. Again, so that will take us to the end of sort of the core tools and techniques from complex analysis. I mean, or what I think is really essential to a first course in complex analysis. And then there's, as I mentioned before, there's a few things we can explore afterwards. And what I want to try is to get as much of the last 2 weeks as possible to sort of explore other directions and look at applications of these ideas and influences that it has in other fields and so on and so forth. Okay, so this is sort of the plan. And then we'll see exactly what, I haven't quite decided what we should do. I might do another survey again, but whenever I do the surveys, they're always quite split. I mean, I guess on one way that's good. But one option is to, so what I'd like to convey at least 2 things. So I guess there's many things that would be nice to convey, but there's 3 things that I think are maybe important. One is, right, keeping in mind that we've already conveyed the notions of, right, the idea that you can use things like Cauchy theorem to say something about geometric or topological properties of at least domains in the complex plane, right? And the ideas that get into algebraic topology and so on. Right, then there's a few other things, which is that complex analysis can be used to compute actually integrals over the reals. Okay? And so for integrals over the reals, we'll see a few of those, like a few examples in the exercise classes using argument principle and residue calculus. I mean, in that you just have to work out 2 or 3 examples to get a feel of it, right? So I won't do it in lecture, but you'll see it in exercise class, and there'll be some exercises around it. And then there's 2 other things that I think are very important or would be nice to be able to convey, right? So one is that is that you can use some of these ideas to say things in combinatorics, for example, right? And that there's maybe in order to attempt to convey this, I'll define and describe the gamma function, right? So it's sort of a complex, nice complex function that sort of extends the factorial in a way, right? That now it becomes not only valid for integers, but for complex numbers. Turns out it has some nice properties. And it's through complex analysis that you can prove things like Stirling's formula and so on, which you may have used already in combinatorics. I'm not sure we'll have time to prove Stirling's formula, but at least maybe I'll define the gamma function and you'll see some of its properties and like how it can be handled with complex analysis. Another thing that would be nice to talk about, and I'll try, is to talk about Riemann zeta function, right? And how it can say things about number theory, and in particular about the prime numbers. So that's again, a very nice complex function, right? That's defined as a certain series that I'll describe at some point. Maybe will show up in an exercise class. And then properties of this function that can be derived using complex analysis can get even to the so-called prime number theorem, right? So in particular, showing sort of measuring asymptotically how many primes there are and up until a certain number x, right? And so this was I believe this was actually conjectured the first time maybe by Gauss even. And the proof is, or the most natural proof uses complex analysis, right? It's just about properties of the Riemann zeta function. And then once you see that, you can see, or at least maybe appreciate more, the importance of the Riemann hypothesis, right? One of the most important open problems in mathematics. And what it says, and then what it says is actually something, very much in the language of complex analysis. So what I'll try to do is maybe not to do either of these things fully, but at least convey that these are two applications of complex analysis and sort of show you the kind of tools that go into it and so on. So that's my plan for the last 2 weeks. And then we'll probably move a little faster, right? Because it's sort of not quite as core, but just to show you some applications and inspire you to look into other things in this area. Another thing that is worth mentioning, even though I won't talk much about it, is, I mean, we already talked a little bit about the fact that if I have an analytic function, right, that if I see it as a map from a domain to say some other set, then it is a conformal map, that it keeps angles, right, between lines. And so there's this area of so-called conformal geometry and so on. So you can now ask what sets, like as you map from a set to another set with an analytic function, because all these properties gets maintained, you can potentially learn from one set by looking at things in the other, right? If you find a good mapping. And so a very natural question is which sets, which domains can be mapped to one another, right? And there's this very nice theorem, this Riemann mapping theorem, that says that most domains actually can be mapped, say, even into a disk, right? Of course, like by now you should realize that you need things like simply connected and so on. And there's a theorem capturing all of this in the heart of conformal geometry, right? So these are things that if you're interested in these, complex analysis and learning more, I highly recommend going and reading in these directions. Then there's applications in sort of, applied math and so on. I won't talk quite as much about those, but we'll see what we can do in the last 2 weeks. And if you have suggestions of things you want to see, please write in the forum, write me an email. I mean, the last 2 weeks, I really want them to be a bit more free and for us to have a bit more fun just looking at some nice, inspiring applications. Okay, so before we get to the last 2 weeks, there's still some math we have to do, right? We still have to develop some tools, so let's try to do this week.